This is Unit 4, Multiple Integrals, Section 15.2, Double Integrals over General Regions. For single integrals, the region over which we integrate is always an integral. But for double integrals, we want to be able to integrate a function f, not just over rectangles, but also over regions D of a more general shape, such as the one illustrated in Figure 1. So we begin by supposing that region D is a bounded region, which means that we can enclose D in a rectangular region as shown. Then we're going to define a new function, f, that has a domain of R such that capital F of xy is going to be little f of xy, provided that xy is contained in D. Then that function is going to be 0 for xy contained in R, but not contained in D. So if f is integrable over R, then we're going to define the double integral then over region D, f of xy dA is equal to then the double integral over the region R of capital F of xy dA, where f is given as shown in the equation above. This definition makes sense because R is a rectangle, and so that capital F of xy has already been previously defined. So the procedure that we've used is reasonable because the values of f of xy are 0 here, where when xy lies outside D, and so they contribute nothing to the integral. This means that it doesn't matter what rectangle R we use, so long as it contains D. And in the case where the f of xy is little f of xy is greater than or equal to 0, we can still interpret the double integral as the volume of the solid that lies above D, and under the surface, z equals f of xy, or the graph of f. So you can see that this is reasonable by comparing the graphs of f, little f, and big F in the figures 3 and 4, and remembering that the double integral over the region R of capital F of xy dA is going to be the volume under the graph of f. Figure 4 also shows that f is likely to have discontinuities at the boundary points of D. Nonetheless, if f is continuous on D and the boundary curve of D is what's called well-behaved, then it can be shown that the double integral exists, and therefore the double integral over D also exists. In particular, this is the case for what we're going to call type 1 and type 2 regions. A plane region D is said to be of type 1 if it lies between the graphs of two continuous functions of x. So we have type 1, we have D is defined as xy such that x is between A and B, and y is between g sub 1 of x and g sub 2 of x, where g1 of x and g2 of x are continuous on the closed interval a to b. And some examples of type 1 regions are shown in Figure 5. In order to evaluate our double integral over region D for type 1 regions, we're going to choose a rectangle A to B cross C to D that contains D as shown in Figure 6. and we're going to be let f be the function, capital F be the function as shown previously. That is, capital F agrees with little f on D, and that capital F is equal to 0 on outside of D. Then we have by Fubini's theorem, we have the double integral over region R of f of xy dA is equal to the region A to B, C to D, D of f of xy dy dx. Now, we know that f of xy equals 0 if y is less than g1 of x, or y is greater than g2 of x, because then xy, for example, is outside of D. So therefore, we can rewrite the integral from C to D of f of xy dy is equal to the integral from g sub 1 of x to g sub 2 of x of f of xy dy, which then is equal to the integral of g1 of x to g2 of x of little f of xy dy, because we know that f of x, capital F of xy, is equal to little f of xy when g1 of x is less than or equal to y, which is less than or equal to g sub 2 of x. Thus, we have the following formula that enables us to evaluate the double integral as an iterated integral. So, if f is continuous on a type 1 region such that D is defined as xy such that A is between, or x is between A and B, and y is between g of 1 of x and g of 2 of x, then our double integral over D of f of xy dA is equal to the integral from A to B and the integral from g sub 1 of x to g sub 2 of x of f of xy dy dx. And the integral on the right side of this equation is an iterated integral, except that in the inner integral, we regard x as being constant, not only in f of xy, but also in the limits of integration, g of sub 1 of x and g sub 2 of x. We can also consider plane regions of type 2, which can be expressed as where D is defined as a function x, y, such that y is between C and D, and x is between some function h sub 1 of y and h sub 2 of y, where h1 and h2 are continuous. Two such regions are illustrated as shown in Figure 7. So using the same methods for type 1 regions, we can show then that the double integral over D of f of x, y, dA is going to be the integral from C to D and the integral from h sub 1 of x to h sub 2 of x of f of x, y, dx dy, where D is a type 2 region. So let's take a look at example 1. So we're going to evaluate the double integral x plus 2y dA, where D is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. So similar to when we did single variable, we need to find our limits of integration. So we know that the parabolas intersect when 2x squared equals 1 plus x squared. That is, x squared is equal to 1, and so x equals plus or minus 1. We note that the region D, as shown in figure 8, is a type 1 region, but not a type 2 region. And there's a possibility that it could be both of them. But we know that this is a type 1 region. So therefore, we have that D is defined as all points x and y such that x is between -1 and 1, and y is between 2x squared and 1 plus x squared. So, since the lower boundary is y equals 2x squared, and the upper boundary is y equals 1 plus x squared, we then have our double integral over d of x plus 2y dA is equal to the integral from -1 to 1 and 2x squared to 1 plus x squared, x plus 2y, and we're integrating with respect to y first, and then x, which gives us then the integral from -1 to 1. This becomes xy plus y squared, which we are evaluating from y equals 2x squared to y equals 1 plus x squared dx. Continuing this, we have -1 to 1, and then we have x times 1 plus x squared plus 1 plus x squared quantity squared minus x times 2x squared minus 2x squared quantity squared dx. So as we continue to simplify this, this becomes the integral from -1 to 1 of -3x to the 4th minus x cubed plus 2x squared plus x plus 1 dx. When we integrate that, we have -3/5 x to the 5th minus 1/4 x to the 4th plus 2/3 x cubed plus 1/2 x squared plus x, evaluated from -1 to 1, which then gives us 32 over 15. Similar to single variable, we have properties that are applied to double integrals. We are going to assume that all of the following integrals that we have exist. For rectangular regions D, the first three properties can be proved in the same manner. And then for general regions, the properties will follow from our description of how to find for general regions. So we have property 6 is that the sum of the two integrals is equal to, or the integral of the sum is equal to the sum of the two integrals. Again, if we have a constant times an integral, we can pull that constant outside. If our function f of xy is greater than or equal to g of xy for all xy in the region, then the integral over the region D of f of xy is going to be greater than or equal to the integral of g of xy. The next property of double integrals is similar to the property of single integrals that was given by this equation. If you recall, we could have the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. If, as shown in figure 17, if D is defined as a union of D1 and D2, where they don't overlap except perhaps on their boundaries, then we have the property over in defined with property 9, that the double integral over the region D can be defined as the sum of the integral over D1 and the integral over D2. So this property can be used to evaluate double integrals over regions D that are neither type 1 nor type 2, but can be expressed as a union of regions of type 1 or type 2. As you can see in figure 18, this illustrates the procedure. If we have, as you see in figure 18a, region D is neither type 1 nor type 2. But if we draw a vertical line, we can then define D1 and D2, where D is the union of those two. And then we can see that D1 is going to be a type 1 integral, type 1 region, and D2 is going to be a type 2 region. The next property of integrals says that if we integrate the constant function, f of xy is equal to 1 over a region D, then we're going to get the area of D. Figure 19 illustrates why this equation is true. A solid cylinder whose base is D and whose height is 1 has a volume of the area of D times 1, which is equal to then the area of D. But we know then that we can also write its volume as the double integral over the region D of 1 dA. Finally, we can combine properties 7, 8, and 10 for the following property. If f of xy is between little m and big M for all xy in D, then we have that little m times the area of region D is going to be less than or equal to the integral, double integral of f of xy dA, and then less than or equal to capital M of the area of region D. So let's go ahead and use that property. It's kind of like the squeeze theorem to estimate the integral of e to the sine x cosine y dA, where D is the disk with the center of the origin and radius 2. So we know then that -1 is less than or equal to sine x, which is less than or equal to 1, and -1 is less than or equal to cosine y, which is also less than or equal to 1. So therefore, we have that -1 is going to be less than or equal to sine x cosine y, which is less than or equal to 1. Therefore, we have that e to the -1 is going to be less than or equal to e to the sine x cosine y, which is less than or equal to e to the first, which we know is e. So, therefore, if we say that m is equal to e to the -1, which we know is 1 over e, and capital M is e, and we know then, since we're talking about a disk with center at the origin and radius 2, our area of that region is going to be pi times 2 squared, or 4 pi. Then we have then that 4 pi over e is less than or equal to the double integral over the region e to the sine x cosine y dA, which is less than or equal to 4 pi times e. Now, there's quite a range between 4 pi over e and 4 pi e, but we did use the squeeze theorem to at least approximate what the volume of that region is.